So is this okay? I tend to walk around. If it drops out, let me know. Put this up here to punch. Anyway, so I'm Dave Scott. I've been with Intel far too long, 1985. I currently have the, hello, it's moving by itself. It's magic. Currently working with OEMs and end users on really large systems. Today I was going to talk a little bit about Intel, a little bit about current products, a little bit about products coming soon, and then a little bit about the challenges of the future, some of which you just heard about, okay? So first thing, if Intel's anything, it's a silicon process technology that's been driving Moore's law for many years, and we actually think we'll keep it up for another 10 years or so, doubling the number of transistors on a die at every couple of years. The other comment is, how do we use that process technology? Well, we build processors primarily. And a few years ago, we made a mistake. We tried to change the processor a lot and the process at the same time. And that turns out to be quite difficult to debug. You're not sure who to blame for the problems you're seeing. Ever since then, we've done what we call the Ticktock Model, which is take the existing processor and shrink it to the new process and use it to debug the process, then bring in the new design on a process that's now stable, okay? So the Intel Core Microarchitecture was the new thing on the 65 nanometer technology, and the products that are out on that are our 4P, what we call MP or scalable systems. This is what it used to be, and this is just a build foil showing how it changed, okay? It went to 4-core with the Core Microarchitecture. You also got, no, we're not going to back up now, excuse me. You also have separate paths to the memory controller, and then the ability to have even more memory. So the four-way nodes, the most important feature for HPC people is if you need large memory nodes, this is the right model to use. Okay. What's happening now, of course, is the new process technology, the 45 nanometer, which has some surprising new stuff. We've been talking about this for several months in the technology meetings. We did changed two things that were important. One was the high gate oxide and the metal gate. If you just took polysilicon and shrank it again, you'd get killed by the leakage current. You had to change what was in the transistors to keep leakage down. So the most important number on this thing is a 10-fold decrease in leakage current, okay? If you didn't have that, you basically couldn't build the parts, right? You could build them, you turn them on, and they melt, right? Which is not very useful, okay? So what did we build with that? We built a processor that was internally known as Harpertown, but it's now the Xeon 5400 series, okay? But it's basically a shrink of Woodcrest/Clovertown. The primary change is we made the cache bigger, and because of the new process technology, you can push the frequency up a bit in the same power envelope. But not a whole lot else changed. Sure, you tweak things here and there. The bigger change, well, actually, first comment is you can take a Harpertown and plug it into the old platform. Okay, you can pull your Clovertowns out, plug in Harpertown, it will work, but you won't get the full advantage of the design without instead changing the platform and putting in what we called the Seeberg chipset, now the 5400 chipset, okay? Seeberg gives you several, am I shouting too much here? I'm starting to get echoes off the wall. Let's see here. I'll put it down here a little further and see how that goes. So Seeberg has first the 24 megabyte Snoop filter to cover the larger caches that Harpertown has. Secondly, it has the PCI Express Gen 2, first instantiation of that from Intel. For graphics people, it means you can use the latest, hottest graphics cards in your workstation. For HPC people, it's primarily you can plug in the higher speed InfiniBand connections and actually get advantage out of it. Okay. The other thing I wanted to comment out, Harpertown's coming out this quarter. Wolfdale, which is a DP version, sort of the equivalent of Woodcrest, But why would you want a DP version when you can have a 4P version? And the primary issues there come from, are you getting any value out of the cores? And if you don't get much value out of the cores, do you want them? Normally, yes, I might get value out of them. But if you're paying large license fees from ISVs, you may not want them, right? If the extra cores get you 10% extra performance for your application, but they double the cost, that may not be a cost-effective choice. So the ability to, so we expect some people may decide to go with the dual core, but most of the people I expect will go with the 4-core version. Okay, coming next, right, you debug the process technology with a shrink, then you do the new design, okay? New design first coming out sometime next year. Code name is called Nehalem. It doesn't yet have a Xeon number, but by the time we introduce it, it will, okay? This is a change of microarchitecture and change of platform architecture. Okay. So the OEMs will get to design new boards. Okay. This is where we introduce our Quick Path Interconnect. Again, the code name used to be CSI, but the marketing name is now Quick Path, so I need to practice that. And the integrated memory controller and lots of other new features, run faster. But it's not here yet, okay? And you always hear about, well, if you wait a year, things will be better. And that's always true, okay? So at some point, you just have to decide, I'm going to buy, yeah, I've got the budget now, I'm going to buy something, okay? So here's sort of the full product roadmap picture in the 4 segments as Intel defines it. Up at the top is the mission-critical 9000 series. That's titanium. It's primarily targeted at the business applications that must never go down, right? So they put a lot of reliability and redundancy in there. And when you do that, it turns out you're not concentrating on how fast it goes. You know, HPC primary use of titanium is in large shared memory systems that OEMs have implemented. But if you actually look at the performance per socket, you're better off with DP blades. The expandable is our MP version, right? Currently Canlan platform with the Tigerton processor that I showed you the picture of. Coming next year will be Dunnington. The efficient performance, which is the new name of the DP boards, right? Basically, new technology comes out in DP land first. So you're always getting the highest performance per clock rate per whatever, okay? We're currently just coming out with Stokely. Nehalem will come out next year. We also have what Intel calls entry, which is basically UP systems. Why would you want a UP system? Well, if your application is sufficiently memory bound, you will actually do better with UP systems than with DP systems. And in addition to that, but then you say, but by density, right? My number of processors per board is going down. So like compute density is going down. But then, of course, we come out with the half-size UP system. So you can get your density back up. But then, of course, you've also come out with the half-size DP system. So you have this plethora of choices, and whatever makes the most sense for your application and your environment. Okay. Now, of course, the roadmap goes rather beyond this, okay, out to here or beyond. But I'm not allowed to say that in this level of audience. If your project needs to understand what's out here, talk to an Intel representative. We can get you a more detailed roadmap discussion, okay? Other things, Intel Optical Cables. Product is out. You'll see the demo. In fact, it was mentioned earlier, right? The visualization demo running between the Intel booth and the Sun booth will have Intel Optical Cables connecting them. This is the kind of product that salesmen love, okay? It plugs into the same socket, right? And it just works. And it works longer. So you can go 100 meters with these cables if you want. Come take a look at them. They're also thinner, they bend easier, all kinds of good things about these cables. So come by our booths, take a look at them, okay? The other thing Intel does is software. In fact, the largest single business group at Intel is the software engineering team, okay? We have several hardware teams, but there's a surprising number of software engineers at Intel, and they produce a large amount of really good software, okay? The Intel compilers, the node-level performance analysis and tuning tools, math libraries, the cluster-level performance analysis and tuning tools, Intel MPI, and thing recently coming out is Intel Cluster Ready. How many of you have built a cluster by hand? It's surprisingly tricky, okay? How many of you are ISV software vendors trying to support clusters in the field? That's actually even harder, right? Because every cluster is different. They have a different network. They have a different process, different MPI stack. So how do you know that that software will run on your cluster? And the answer is, if the ISV and the cluster are Intel Cluster Ready, it is certified that the software will run when it arrives. That's the end of current products. I now want to say a few words about Intel's foray into what about future stuff, right? More cores, what a surprise, okay? This is the teraflop chip's been out for a while, but I want to use it as an example describing some of the issues. It is not a product. It will never be a product. You cannot buy them. And in fact, if you could buy them, you wouldn't really want to because there's no I/O, it's only single precision, it's not an IA core, none of the tools work, all the things, so it's not what you want. But it's in fact got lots of interesting stuff. How do you connect cores, by the way? Well, if you have 2 cores or even 4 cores, you can connect them to a shared cache. But if you have, say, 16 cores, good luck. If you have 80 cores, no chance. So one of the things this chip was designed to test was the network. There's actually a 2D network. It's actually 2.5D, which I'll talk about in a second. So you got a whole bunch of cores and a router and connections between the cores. So you can, and it's still coherent. You can pass cache lines around. Okay. There's also issues like power delivery and clock. How do you get a clock to 80 cores and make sure it's that the jitter's not too bad? And the answer is we didn't try. The clocking we do here is what they call mesocronous clocking. We guaranteed that the frequency would be the same at every core, but there was no jitter control. So the network between the cores had to work out how to deal with the jitter between the clocks. Right? Lots of interesting work here. Power management, right? How do you turn pieces off or slow them down or bring them up again? Well, if you turn the network off, it's a bit bad, but turning the core off could be a good thing, right? And they actually have demos of this thing where you have this application running at a certain speed, and you turn more and more of the cores off, and the speed goes down, but it still works, right? And the power is going down at the same time. Okay. I mentioned this 2.5D network because of the real problem. Sticking floating point units on a die, connecting is a little exciting. Sticking them on a die is easy. You can get lots of them on a die these days. How do you get the data in? One of the things Intel's looking at is stacked memory. And so those 80 routers actually had a 5th port going up, and you could slam a DRAM on it, and you now have quite a bit of memory bandwidth. Now, it's not a standard DRAM. There's all kinds of issues with like getting power through it and having the ports at the right place and thinning the die so you can actually smack it together. Okay. But it's interesting. It's research, right? It's not a product yet. Bandwidth is going to be the issue, both to memory and then from memory to the other processors or out to disk or whatever, right? There are issues at every level. Okay. So Two other things we're looking at. One is trying to get signals off the top of a socket. It turns out that optimizing pins for high-speed I/O and optimizing pins for power are almost contradictory. And if you can take the I/O off, take the signals off the top, you can then have a much more optimized configuration. The other thing, how do you get to faraway places? Well, I mentioned the Intel optical cables, but you could save a fair amount of power if you could suck the optical interface all the way onto the die, or at least into the package, and do it with silicon photonics instead of hybrid photonics, which is what the cables do. Intel's proven they can build all the pieces, right? The question is, can they do it cheaply enough? It's a volume manufacturing problem now, not a technology problem. So there's work going on. There's trying to build not just working things, but being able to build millions of them at the right price point. Finally, there's power. Jay was talking about power. It's only going to get worse. Intel's doing the best they can at the interior levels, but there are issues at power delivery and cooling that you heard about earlier. Power's gone from being a background item to being one of your, first-class budget items, right? Okay, so the idea, things that's coming in chips. What we're doing now, going from 2 to 4 to 6 to 8 to 10, we call multicore. But many-core is coming. There will be products based on the kind of design of that teraflop test chip with lots of simpler cores. It'll put even more stress on the memory bandwidth and the programming model. There's lifetime employment here for application people and tools people for how to take advantage of a system that may have 1 million cores. That's it. Thank you. Any questions?